Hey friends! Okay, so if you want to know where that 2.5% came from without running data, which is, running the data is how statistics works. You run experiments, you collect data, and then you report back on it. In a case like this, though, because we know the composition of the card deck, we can actually get the percentage that we used Excel to get. We can get the percentage via calculations, using the same kind of calculations that we used in class today. I did them kind of quick because they're not a big part of Math 243 anymore. They're more of a part of Math 105, and some of you didn't take 105 with me, and that's totally fine. But probability, and we're going to have a whole project based on this at the end of next week, but just to give you an introduction to it, the probability of something happening is just the rate of time at which it happens, or the rate of the time which it happens. So if somebody says something has a 50% probability, that just means over time it happens 50% of the time. Doesn't mean it happens every half of the time. We mentioned that today with the coins, right? Like, if you flip 50-50 on a coin, doesn't mean it goes heads, tails, heads, tails, heads, tails. Because that wouldn't be 50% probability. That would be 50% probability at first, and then 100% of the time you would know what was going to happen next, right? If it flipped heads, then 100% of the time you know it would flip tails next, and then 100% of the time you know it would flip heads, and then 100 tails, which is exactly not how coins work, right? Coins over a long period of flips will flip half heads and half tails. Cards are similar in that when you pull that first card off the deck, it's 50-50 because half the deck is red and half the deck is black. To figure out the rate at which we can pull 5 red cards off the top of a fair deck, though, and I'm going to drop some ideas on you now that we'll revisit in the first project next week. What you have to do is, to figure out the rate of time something happens, let's think back to a coin. You say that a coin flips heads 50% of the time. 50% is another way of saying 1/2. That's 50% as a fraction. I prefer fractions sometimes with this because it's easier to visualize. That means there's one way to flip heads and 2 ways for the coin to flip overall. That makes perfect sense. One way to flip heads, 2 ways for the coin to flip overall, and both of those ways are equally likely, which is why it's 1/2. If you envision another experiment, like rolling a 6-sided die, and you were betting on, I don't know, so you bet on 5, then there's a 1 in 6 chance that you're going to get it right, because there are 6 equally likely outcomes, and only one of them is a 5. Again, we're going through this kind of quickly because we'll see this again in the project next week. For the cards, it's a little trickier because there's 5 individual probabilities. The first one is the chance that the first one was red. Now, we know what the answer to that is. We know it's 50-50 because half the deck is red and half the deck is black. I'm going to write it in a different way, though, for purposes of illustration. It's 26 out of 52 because there are 52 cards in the deck and 26 of them are red. The second card being red, assuming that the first one was red, that's the key. I'm not going to write that here. We'll write it down in the project next week. The second card being red, assuming that the first one was red, is 25 out of 51. 25 out of 51. The third card being red, assuming that the first 2 were already red, hopefully you see what's going to happen now, it's going to be 24 out of 50. The fourth card being red is going to go down again, 23 out of 49. And the fifth card being red is going to be 22 out of 48. So hopefully you can see what's happening. We're removing one thing each time, but that one thing has 2 characteristics. First of all, it's a card. So every time we go back to the deck to draw, we're removing one of the potential outcomes of the experiment. We're also decreasing the desirable outcomes because we're pulling one of the red cards out each time. So this one right here is exactly equal to 50%. This one down here, I can't do that in my head. Let's see, 48. If it were 24 out of 48, it would be 50%. So it's 1/24 lower than that. So it's a smidge under 50%. And we discussed that in class. These are all very close to 50%, but they're decreasing, right? They're getting smaller each time. In class, I talked to a couple of you who noticed that if you were to multiply 1/2 times itself 5 times, you get 1 out of 32, which is really, really close to 2.5%. You can apply that same principle, but instead of using the 1/2s, because these aren't all 1/2s, you can just simply multiply these 5 fractions together. Now you might ask yourself, why multiply? I'm going to punt the answer to that one to week, I believe it's 7. Whenever your second project is, we'll justify why you multiply. So trust me for now, and trust me that it works, and trust me that we will get to it. But I wanted to address this in class just because somebody brought it up, and it was a great question, and I think it deserves an answer timely. So if you multiply 26 over 52 times 25 over 51 times 24 over 50 times 23 over 49 times 22 over 48, boom! That's where that percentage comes from that we were quoting in class today. So I just wanted to let you know there is good mathematics backing up that 2.5%. I also want you to know it's not super important for Math 243 because the fiction of this problem when you try to apply it to the overall world around you is we actually know the entire population in this problem. We know there's only 52 cards in the deck. Now this is great for playing poker or playing blackjack or doing something like that. It's not great if you're doing something like studying ADHD in middle school boys, because you don't know what that population is. You don't even know what the entire population of middle school boys is, let alone those that have ADHD. So the only way you're going to be able to do it is to go out and draw a sample like we were doing in Excel today. So I like to lean more on the Excel method that we were doing today, not necessarily in Excel, but the data collection in general, which we'll do more of next time. And use this as an introduction to that, but realize that this mathematical kind of trickery that we just did is limited to things that we know the entire population of. Okay, we'll see you on Thursday.